Hey, you guys, hope you're having a good time at home. I'm really glad that I had a chance on Friday to introduce the chapter to you. You know we're doing linear regression, you know we're doing LSRLs, you know we're looking at X and Y variables. There are different types of conditions you have to check for these. So this is our very first write-up. This one is a confidence interval, and as you can see, I've given you a lot of stuff to look at and analyze here, and I also want you to beware that we are going to be using calculators and stuff for these videos, so it's just really important for you guys that as soon as you have a question that comes up, please send me an email or contact me somehow. Don't forget your questions. They're great questions. I'll try and post answers to Schoology, but I want to, do my best to help you guys through this. This is our last chapter. We've only got a couple videos here that I'm going to have to go through, so anyways, I'm just going to go right into it, and I do have everything written out already at the bottom, so you can always pause and copy stuff down, but it's going to help me like quicker talk through stuff that you need to say. So pause the video if I go too fast. By all means, pause, copy down, and then listen very closely to the explanations, okay? So we've got these two AP Stats students, and they're taking carnations, which is a type of flower, at a grocery store. And they're trying to figure out if they can grow better if you put sugar in the water. I never knew this was a thing until I started looking at this problem. But what we have is we have 12 identical vases with exactly the same amount of water in each vase. And 1 tablespoon of sugar goes into 3 vases. 2 tablespoons of sugar goes into 3 vases. 3 tablespoons in 3 vases. And then the other 3, they put 0 sugar. So here's our data table organized with tablespoons of sugar for all 12 of the vases, and how long these flowers were fresh. So I'm not exactly sure how they measured how fresh the flowers looked, but whatever, we're just moving on. Okay, remember that we also have this is called a regression output here. So important information, the coefficient, the constant, this is your y-intercept, the 181.2. The coefficient on the sugar, which is the x value, is 15.2. That's your slope. And we're also going to be using this S value, and we will use the R squared later. So we have some important info here. Just keep that kind of thing in mind. Okay, and the standard error of remember this is the slope number, so this column and this column intersect here. This is the SE sub B that we will use in a formula later also. So make sure that you're aware, picking out some of this important data from the table that I give you, the regression output, if you will. Okay, let's just go right into the question being asked. Construct and interpret an interval, a 99% confidence interval for the slope. So we're trying to estimate the slope. It appears here in our original scatter plot that we do have a positive correlation between sugar and freshness. So as the sugar increases, it does appear as though the freshness lasts longer. Okay, but let's actually test it and see if it's just a fluke. Did this just happen by chance, or do we have reason to believe that this will happen, that sugar actually does impact the freshness? So first you define your stuff. Always define the x and the y. So you know that we're looking at an x value and a y value here, and that's what's forming our scatter plot. So you need to define the x and the y. So the x is the sugar content, be as specific as possible. Tablespoons, the y is the freshness that was measured in hours. You can get that from the table or from the wording of the question way above. And also define this beta, it's like cursive B. That's the true slope that we're trying to estimate here. So we're trying to estimate by coming up with an interval of what the true slope of this line is, and we just did a sample, and it's the true slope of the regression line of y versus x. If you remember from chapter 3, you always do y versus x, so freshness versus sugar. And then the sample LSRL is the last thing that you need to have in your defined stuff. So there's 4 things to define: x, y, the beta, and the sample LSRL. So remember, this number is your y-intercept and this number is your slope. And make sure you've got a y hat on your y. That is really important. Here's our introduction sentence. Remember, you're using a keyword here, estimate. We're estimating beta. Beta is the true slope of the regression line. And we do not know the sigma. Again, we're just basing it off just these 12 bunches of flowers in the example. So that's the same thing as previous chapters. When you don't know the sigma, then you use a T. And this is a 99% confidence interval. So Anyways, let's go through our, I told you I have everything written out. Pause the video, don't panic. I just want my handwriting to be nice, and I want to be able to go through this quicker than just pausing and writing everything. Anyway, remember liner, L-I-N-E-R. Those are our 5 different condition checks that we have to go through for this chapter. And remember, what you're looking at is the scatter plots and stuff that I gave you above, so I guess I shouldn't have zoomed so much. Linear, there's 2 things you're looking at. The original scatter plot, it does show a strong positive linear relationship between y and x, so that's this scatter plot right here, the sugar and the freshness. I would definitely say that's strong and positive and linear. It's not curved, it's not like a no association situation. That is a pretty good looking scatter plot if I've ever seen one. So I'm going to mention that. I'm also going to mention the residual plot here. It does have a consistent random scatter. No obvious curve or pattern. Remember, that's what a residual plot is supposed to look like. Sometimes your line overestimates and sometimes your line underestimates. And not always do the dots fall really close to the line. Sometimes it's farther off. So those are all the things you're looking at the residual plot for. The independence condition, they were kept in different vases. So one freshness of the flower doesn't impact the other flowers. We are doing an experiment here, so you don't need to mention anything about the 10% condition. We didn't take a sample of flowers. We just used all of our flowers. Okay, so keep that in mind. When it's an experiment, you don't have to check the 10% condition. For normality, let's see, they gave me a histogram here. Yeah, looks kind of left skewed, okay, but I'm going to go with roughly bell-shaped. This is the residuals here. Kind of bell-shaped, I guess. It's okay to mention like a slight left skew. Remember, you're looking for extreme stuff. That would make the normal condition fail. It doesn't appear as though they have any outliers. Another thing that we have checked in the past was the normal probability plot. That was not given up here. That's why I'm not mentioning it. But if I did give you the normal probability plot, remember that's the z-scores on the y-axis and the x values on the x-axis. And that's supposed to be approximately linear. And so that would be a good thing to mention if I gave it to you. But if I didn't give it to you, then you don't have to talk about it, okay? So that's why I wrote this right here. Equal variance, remember that's when you're looking at the residual plot and you're making sure that the residuals aren't really big at the beginning and then get a lot smaller, or vice versa. They could start out really small and then get really, really big. That would be something that would fail the equal variance condition check. So we have a consistent random scatter throughout the residual plot. Again, you can say that the residuals don't tend to increase or decrease as the x value increases. Say something like that about equal variance, okay? And then lastly, random. We already know how to do that. The flowers are randomly assigned to treatments. Make sure that you say what is random about these flowers. We did not take a random sample. We randomly assigned them to the treatments. Okay, finally, let's get into the math. Remember, the degrees of freedom is n-2, and this is the only chapter that it's n-2, and the way that I remember that it's n-2 is because we're measuring 2 variables together. That's why I remember it as n-2. Anyway, so we had 12 sets of flowers. Minus 2 gives us 10 for the degrees of freedom. Here is your formula for the statistic plus or minus critical value standard deviation of statistic. It's a little bit different, but in words on the formula sheet, remember, hey, that's in Schoology. It's in the copy of tables and formulas for the AP exam. It's its own folder in the textbook folder. You can look that up. But in words, it says statistic plus or minus critical value, which is your T star in this case, because we don't know the sigma. And then SE sub B is the standard deviation of the statistic for this chapter. Okay, so the slope that we used for our sample of flowers is this slope right here. It's also from the regression output way above that I already mentioned. So 15.2 goes there, plus or minus. How do you find this T star? Well, you do inverse T in the calculator, and it's 0.005 on each tail, since this is a 99% confidence interval, and then it'll ask for degrees of freedom also. So remember, you're going into distributions, and then distributions, I believe, is F5. There's an inverse menu doing inverse T. So do left tail area and then degrees of freedom, and it will give you this as your T star. The SE sub B is also above. I pointed that out earlier. That is this number right here. It's the standard error of the slope, the X value, which is the sugar. So standard error and with the slope number, like where it intersects, okay, right there, 1.943. That is the number that you fill in for the standard deviation of the statistic. Anyway, so crunch that number and you end up with this as your confidence interval, and then you write your sentence to conclude. We're 99% confident that the flower freshness time increases between this much and this much hours. Put a unit on that since we know what the unit is for this experiment. For each additional tablespoon of sugar added. So for every tablespoon that we add of sugar into the water, supposedly the freshness increases. Can we feel confident predicting the hours of freshness if 10 tablespoons of sugar are used? So sure, someone who is not paying close attention could plug in 10 wherever they wanted to into this equation right here. Plug in 10, plug in whatever number you want. Mathematically, you can always come up with an answer, but is it going to make sense, my AP Stats students? No, that would be extrapolating. Okay, hopefully you knew that before you saw my writing, but you don't want to extrapolate. We only did our experiment based on 0 to 3 tablespoons. We cannot assume that pattern continues. It's the same exact thing we've talked about with growing. When you're a baby and a toddler and a child, you grow so fast. Are you growing that fast right now as a high school student? No, it does not continue. Extrapolating is very bad. Okay. Also, let's see. So no calculator work needed for this question except for finding the t. I think I'm going to skip around a little tiny bit. Can you flip forward like a whole page? I'm going to do that example that you're skipping over as a different video because it's a little bit longer and it involves some calculator work, but I just want to finish this section with this example. What we have here is a random sample of 11 Hondas, and these are 2002 to 2006 models. From CarMax with number of miles driven and the advertised price. So we have a 95% confidence interval. So don't you agree probably that as you drive the car, so number of miles and price, if the car has like 0 miles on it, it's brand new, it's pretty expensive. But if the car has a lot of miles on it, isn't it like not as expensive? Doesn't that make sense? So negative linear relationship here. Okay, we've got, for some reason, the hoe got pushed up over the other word, so it's a little hard to see, sorry. Anyway, the hoe says that the beta equals 0. So remember, your hoe is always an equation equaling 0, assuming no difference. In this case, assuming no useful linear relationship between these two variables. And the ha would be there is a useful relationship, meaning the slope is not 0. In this case, if this is our interval and the entire interval is negative, doesn't that give us evidence that the slope is negative? Like if you were predicting, you would write an equation saying, we are 95% confident that the true slope is between these two numbers. Okay, so every number in between these two numbers is negative. And so that's what's saying is that we're pretty confident that the slope between number of miles and price is negative. And so in this case, what conclusion can we draw at the 0.05 level? Remember that you're always looking at your interval for whether or not 0 is included in there. So in this case, since 0 is not included in the interval, we probably want to reject the hoe. We're thinking that the slope is not 0. We're thinking that it's something else. And in this case, we are saying that there is a useful negative relationship because our entire interval is negative, between price of a car and number of miles driven. And hey, in common sense, that makes sense. As you increase the number of miles, the price of the car goes down. Nobody wants to buy a car with 200,000 miles on it because you don't think you're going to get another mile out of it. But if the car has 0 miles on it at the y-intercept, in this case, that does make sense in context to have a y-intercept for 0 miles driven. That means it's a brand new car. The price is as high as it's ever going to be because nobody's ever driven it. It appears as though number of miles driven increases, the price of the car decreases. So that's just something to remind you that we are going to still be connecting like hoes and ha's and significance tests to confidence intervals here. The confidence interval should give you some info about whether or not you're going to be rejecting or failing to reject. In this case, we would want to reject the hoe because we do think that the slope is negative. And the ha here says that the slope is not 0. Anyways, that's all for now. Fill out your section 12.2 reading guide. I really highly encourage you guys now more than ever to spend a little bit of time reading your stats textbook. It's just going to help because this is going to be a tough time for us to get through this chapter. So whatever questions you have over this video, please send them to me. I'll get right back to you as soon as I can. And there's going to be more videos for the rest of the week, okay? Have a great day. I'll see you soon, and I miss you all.